Welcome to our CST232 Operating System Assignment 2 presentation. We are Group 3. I'm Ling Xingqi, the leader of our group. Here are our group members. In modern operating systems, multiple threads often run concurrently. Without proper synchronization, this can lead to rest conditions when shared resources are accessed at the same time. In this presentation, we will first demonstrate how mutual exclusion is achieved using the test and set instruction. Then, we will move on to semaphore, which provide a more efficient and a fair synchronization mechanism. Finally, we will discuss several disk scheduling strategies and compare their performance characteristics.
My name is Pei Wan Ting. With metric number 2330-2517, I will be presenting question 1 from our assignment 2 on test and set synchronization. I will be covering task 1, which is the implementation of the test and set function, and task 2, which demonstrate mutual exclusion using multiple threads. First, let me introduce test and set. Test and set is a fundamental synchronization mechanism that ensures only one thread can enter a critical section at a time. Its purpose is to manage access to shared resources and enforce mutual exclusion, preventing rest conditions where multiple threads trying to access the same data simultaneously. Here is our test and set implementation. We initialize the log as a list containing 0. We use a list instead of a simple integer because lists in Python are mutable and can be passed by reference, allowing all threads to share and modify the same log variable. The test and set function perform three operations as a single atomic action. We use Python's threading log to guarantee atomicity, ensuring that only one thread can execute this function at any given time. Inside the log, we perform three steps. First, we read the current log value from the list and store it in O value. Second, we set the log to 1 by modifying the list element, which indicates that the critical section is now busy. Third, we return the O value that we saved earlier. The return value logic is important. If the function returns 0, the log was free and the thread has successfully acquired it. If it returns 1, the log is already in use by another thread. This effectively simulates a hardware test and set instruction. In task 2, we demonstrate mutual exclusion. Here we have two key functions, acquire and release. The acquire function repeatedly calls test and set in a loop until the log becomes available. If test and set return 1, the log is busy, so the thread must wait. When it returns 0, the log is free and the thread can enter the critical section. The release function is simpler. It sets the log value back to 0, which allows the next waiting thread to proceed and acquire the log. These two functions work together to control access to the critical section. This slide shows the critical section function that each of our 5 threads will execute. When a thread starts, it first calls acquire to get the log. This ensures the thread waits until the log is available. Once the thread successfully acquires the log, it brings its thread ID to confirm it has entered the critical section. Next, we use time sleep for 1.5 seconds to simulate computational work being performed while the thread holds the log. After completing its work, the thread called release. This sets the log back to 0, allowing the next waiting thread to enter the critical section. All 5 threads in our program execute this same function, which allows us to test mutual exclusion with concurrent execution. Here is our main execution setup. We start by initializing the log as 0, which means it is free. We use a list so the log can be passed by reference and modified by all threads. We create an empty list called thread to store our thread object. Then we use a for loop to create 5 concurrent threads. Each thread is created with a unique ID and the shared log variable. We call thread start to begin execution for each thread. The small time slip of 0.1 second creates a slight delay between thread start. Finally, we use thread join to block the main program until each thread finishes. This ensures all threads complete their execution before the program exits. This setup allows us to test whether our test and set implementation truly enforce mutual exclusion. Now, let me demonstrate this program in action. I will run the program now. Watch as thread 1 attempts to enter the critical section. It successfully acquired the lock, enter and perform its work for 1.5 seconds. Now it exits and releases the lock. Notice that thread 2 only enter after thread 1 has completely exit. There is no overlap between threads. This sequential pattern continues for threads 3, 4, and 5. Each thread waits its turn before entering the critical section. Looking at the complete output, you can see all 5 threads execute one at a time with clear separation between them. No two threads were ever in the critical section simultaneously. This proved that our test and set implementation successfully maintained mutual exclusion throughout the entire execution. How test and set ensure mutual exclusion? The key is that test and set perform its operation atomically. It reads the log value, set it to 1, and return the old value, all as one indivisible action. This means two threads cannot simultaneously read the log as 0. When a thread called test and set and it returns 0, the log was free and the thread has successfully acquired it. The thread cannot enter the critical section. If it returns 1, the log is already busy. The thread recognizes another thread is using the resource, so it enters a busy waiting loop, repeatedly pulling the log until it becomes available. The log only resets to 0 when the occupying thread finishes and calls the release function. This is the only way for a waiting thread to accrue the log. This guarantees that only one thread can be in the critical section at any time, preventing ray condition and ensuring correct program execution. However, while test and set does enforce mutual exclusion, it has a significant drawback. Busy waiting is highly inefficient. Let me explain the four main problems. First, CPU waste. When a thread busy waits, it repeatedly checks on the log in a time loop while staying in the running state. The CPU dedicates thousands of cycles just to execute this while loop. This is non-productive work. The system is busy but making no real progress. Second, scalability issue. As more threads spin simultaneously, performance worsens dramatically. Multiple spinning threads create massive CPU contention, reducing overall system throughput. Third, single core problems. On a single core system, if the waiting thread is currently running, the log holder cannot execute to release the log. This forces unnecessary context switch and causes significant delay. Finally, priority inversion. A high priority thread might wait for a log held by a low priority thread. This means important tasks get blocked by less important ones, which is drawback from what we want. This is why modern operating systems prefer higher level synchronization mechanisms like semaphore that block threads efficiently without busy waiting.
Next, we will discuss question 2, semaphores. In this slide, I will explain why semaphores are needed. Test and set relies on busy waiting, which wastes CPU resources. Semaphore improve this by using blocking and waking mechanisms. Counting semaphore allows multiple threads to access shared resources, and first-in, first-out ordering helps prevent starvation. This screenshot shows the counting semaphore class. The semaphore maintains a counter, a mutual exclusion lock, and a first-in, first-out waiting queue to control access to shared resources. The semaphore is initialized with a value of 3, meaning up to 3 threads can access the shared resource concurrently. A lock protects the internal state, and the first-in, first-out queue stores waiting threads to ensure fairness. In addition, a condition is used to block and wait threads when resources are unavailable. When a thread calls the wait method, it checks whether a resource slot is available. If no slot is available, the thread is placed into a first-in, first-out queue and put to sleep using a condition variable, avoiding busy waiting. The signal operation releases a resource slot. If there are waiting threads, the semaphore wakes the next thread in first-in, first-out order, ensuring fairness. The semaphore class is later used in tasks to demonstrate concurrent execution and first-in, first-out fairness in practice.
Hi, my name is Ching Xing Yi. Today I'll be presenting the implementation and results for question 2, task 2. I'll be demonstrating how a custom-built counting semaphore in task 1 manages 5 concurrent threads to ensure mutual exclusion and first-in, first-out fairness within a shared buffer environment. So now let's dive into the implementation part. The simulation is driven by the thread job function, which you can see from the yellow box in the slide. I've implemented a print log at the global level, which you can see also from the orange box in the slide. This is essential in multi-threading because the sender output is a shared resource. Without this lock, thread messages will be overlapped, making the logs unreadable. The thread lifecycle is a strict four-step process: request, wait, execute, release. First, the thread sends a request to use one of the slots. Second, it calls semaphore.wait. If our three slots are full, the thread doesn't keep trying to enter. It is moved to a wait queue and put to sleep. This is what we call non-busy waiting. Once a thread enters the critical section, we simulate a task using time.sleep. This represents the thread safely accessing the share buffer. When the task is over, the thread calls semaphore.signal. Think of this as a direct handoff. Instead of just leaving the slot empty for a free-for-all race, the exit thread checks the first in first out queue and specifically wakes up the thread that has been waiting for the longest time. This ensures that every thread gets its turn in the exact order it arrived, which perfectly prevents starvation. In main execution block, we define our environment variables, which is 5 trees as required in this question and the tree slot capacity. This creates a constrained environment where contention is guaranteed. By using t.start in a loop, we launch all threads simultaneously. This forces our semaphore to handle a sudden burst of requests. We then use t.join to synchronize back with the main process, ensuring the program only concludes after every thread has safely released its resource and exit the simulation. To demonstrate task 2, I've integrated the counting semaphore class we built in task 1 into this script. By running the task 1 logic first, we provide the simulation with the necessary synchronization engine. Once initialized, we can observe how the semaphore manages real-time thread contention. So now I will run task 1 and task 2. As I run the code, notice that all 5 threads immediately attempt to acquire a slot. However, because our semaphore is initialized with a value of 3, only thread 1, 2, and 3 are permitted to enter the critical section. So you can see from the output, thread 1, 2, and 3 are permitted to enter the critical section. Now, look at the logs for threads 4 and 5. They print blocking or put to sleep. This confirms that our mutual exclusion logic is working perfectly. The semaphore recognized that no slots were available and safely suspended these threads. Now, as thread 1 finishes its work and call signal, notice that thread 4 is the one that immediately wakes up and enters. It doesn't matter if thread 5 was ready, thread 4 arrived first in our queue, proving our first in first out fairness is active. Finally, as each thread exits, the remaining waiting threads are brought in one by one until the program prints the program is completed message. No threads were lost, no buffer overflow occurred, and the order was strictly maintained. The first key question is, why use a counting semaphore instead of binary one? A binary semaphore is like a tiny cafe with only one chair. It's a one-in, one-out system. If we use that here, we will be wasting our resources because even though we have 3 buffer slots available, only one thread could work at a time. Instead, our counting semaphore acts as a resource manager, much like a cafe with 3 tables. It allows us to maximize throughput, which is the amount of work the system gets done by letting 3 threads work at the same time in parallel. However, it also acts like a safety wall, just like the third customer will have to join a queue until a table opens up. Our semaphore forces the fourth and fifth threads to join a first in first out wait queue. This prevents system overflow and ensures that while we are being efficient, we never exceed the safe capacity of our share buffer. Secondly, how do we prevent starvation? In a standard unlocked race, a fast thread could finish and immediately re-enter, starving slower threads that are still waiting. We prevent this by using a first in first out queue because we store thread condition variables in the collection queue. We create an orderly line. New threads are added to the back and cannot cut the line. By ensuring the oldest waiting thread is always the next one to be woken up, we guarantee that every thread eventually gets its turn, which eliminates starvation entirely. Finally, how does your code ensure mutual exclusion and fairness? Mutual exclusion is ensured because of the internal self-dot log in task 1, which makes the semaphore value updates atomic. Fairness is achieved because the signal operation doesn't just increment a number, it performs a direct notification to the next trace condition variable. This non-busy waiting approach is not only fair but also CPU efficient, as block threads don't consume power while they are waiting. My name is Charlie Ng and my metric number is 23304427. I am in charge of question 3, task 1, understanding disk scheduling and SIG strategies. For this assignment, we will focus on 4 disk strategy such as first come first serve, shortest seek time first, scan, C-scan. So for this part, I will explain about how each strategy works. For first come first serve, requests are served in the order they arrive. The disk head move to each requested track sequentially. For shorter seek time first, the disk head services the request with the track closest to its current position. For scan, the disk head moves in one direction servicing all requests along its path until it reaches the edge of the disk, then reverse direction and continue servicing requests while moving toward the opposite edge. For C-scan, the disk head service requests in one direction only. When it reaches the far edge of the disk, it returns to the beginning edge without servicing requests on the return. Then resume servicing forward from the lowest requested track. For second part, I would like to explain what types of workloads each strategy is best suited for. For first come first serve is light workloads with few I/O requests and low contention. For shorter seek time first is moderate workloads where request distributed is fairly uniform. For scan, light to moderate workloads with requests spread across the disk. For C-scan, moderate to heavy workloads requiring uniform waiting time for requests, such as real-time system. In third part is about one advantage of each approach. For first come first serve, it's simple to implement and fair since requests are served in arrival order. For shorter seek time first, is minimize overall seek time compared to first come first serve, improving performance. For scan, prevents starvation and provides more predictable performance than shorter seek time first. For C-scan, it provides more uniform waiting time for all requests than scan by treating the disk as a circular list. Lastly, we will discuss about one disadvantage of each approach. For first come first serve, it causes large head movement leading to high average seek time and poor performance under heavy load. For shortest seek time first, it causes starvation for requests far from the current head position if closer requests keep arriving. For scan, the disk head moves to these edges even when no request exists there, causing unnecessary movement. For C-scan, it leads to higher seek overhead than scan due to the disk head returning to the beginning edge without servicing requests.
In conclusion, this assignment explored key operating system concepts. Test and set demonstrated mutual exclusion but also showed the inefficiency of busy waiting. Counting semaflow improved efficiency through control concurrency and first-in first-out fairness. These scheduling strategies further highlighted how resource management affects system performance. Overall, proper synchronization is essential for reliable operating systems. That's all for our assignment. Thank you.